Welcome back, everyone. In this video, we're going to be talking about the tension capacity of bolts with some extra discussion on prying action. Our example for this video is going to be a hanger on a beam. Specifically, we're going to be looking at the T part of this hanger, and it's anchored to the beam using 4 bolts. Now, there's 150 kips pulling down on this thing, which means all my bolts are in tension, and the tension demand is going to be 37.5 kips per bolt. So to evaluate my capacity in tension, I'm going to go to table 7-2 in the steel manual. This is essentially just distilling down what's in the spec J3.7. And I need 2 parameters. So I need the bolt designation. This is essentially the material strength. I'm using group 120 for this case because I have A325 bolts. And my bolts are also 7/8 inch diameter, which means my capacity is 40.6 kips. That's greater than 37.5 kips per bolt, and so I'm good. Except there is one thing that we neglected. So if you look at the spec a little bit more closely, it says that the required tensile strength shall include any tension resulting from prying action produced by deformation of the connected parts. It's going to send you back to part 9 of the construction manual, where it discusses this phenomena known as prying action. So the method that I'm going to show you here, I will say, is a little bit different than what is in the steel manual. They will both, however, get you identical results. I find my method to be a little bit more intuitive, and it's checking sort of standard limit states, whereas the manual is more focused on finding the thickness of a plate that doesn't have any prying. Either method works. If you're interested in using both methods, I do have a spreadsheet down in the description that you can download, and you can compare them, and you can see that, in fact, they will get you the same thing. But first, let's talk about what is prying action. So in my case, I looked at just a force, and let's say it's being supported by 2 bolts. So I'll have 2 TR, and my force in the bolts is TR going down. Simple, easy, but not entirely correct, because what's going to happen is that plate is going to deform. So as that plate deforms, there's going to be a contact force, also known as a prying force, that develops right here on the edge of my plate. It's called little QR. So if I put the same load on it, 2TR, we'll find that from statics, this is now TR plus QR, as is this one, TR plus QR. So my demands have just been amplified in those 2 bolts. So I'm going to have a problem if I ignore this and I just stick with my original design. In order to consider this, what we're going to do in this video, and again, this is a little bit different from how the steel manual presents it, is we're going to consider 3 different failure modes. And the first one is where we get to ignore prying. So once again, I'm going to put a force of 2 TR up here, and I'm going to have forces of TR down there and there. Now, in this case, the bolts are going to stretch out enough, and the plate is going to be strong enough such that there is no contact at the corners. So sometimes this is known as the thick plate condition if you have that. Because there's no prying action, I'm essentially done. But in order to ensure this, I need to make sure that my plate remains entirely elastic. In the second case, we're going to look at bolt failure, and now I'm going to have prying. So if I have a force here, we're going to call this force 2T BP. So BP is going to stand for bolt prying in this case. And I am going to develop a prying force here of QR and QR. But now my force in the bolts is going to be the capacity of the bolt, T sub C. And that T sub C is exactly the same T sub C that you look up in table 7-2, and it works both for ASD and LRFD. You are going to include that phi factor or that factor of safety in this number TC. The other thing that's going to be the case is that this is definitely not elastic anymore. So we're going to have plastic hinging right at these locations right here. And that is the location of the highest moment in my plate. The last failure mode is going to be the plate failure, but with prying. And for this, we're going to form 4 plastic hinges, which creates a mechanism. And therefore, the plate will not be able to carry any more load. Now, the load on this, we're going to say, is 2 times TPP, which stands for plate prying. And we'll still have the same prying forces, QR here and QR here. But the force in my bolts, T, is going to be less than the capacity of the bolts. So force T is less than TC. So the idea here that we're going to follow is that first we're going to check to see if we need to consider prying at all. And if we do need to consider prying, we're going to see which of these two failure modes will control. So let's begin with the no prying case. If we're ignoring prying action, we need to make sure that the moment here remains elastic. So our moment there has to be less than our plastic moment capacity, which I'm going to call MP1 at that location. Now we can draw our forces. So this is 2 times TR. And I'm going to very carefully draw these other two forces, TR right here and here. And you'll notice they are not centered on the bolt. They're actually located traditionally on the edge of the bolt hole right there. The purpose of this is to account for the fact that there's not just a straight up force in there, but there's a force and a moment in those bolts due to how this connection bends. So now we can look at a moment arm right here between our force and our peak moment, and that distance is known as B prime. So therefore our moment at that location, M, is going to be TR times B prime. And because M needs to be less than or equal to MP1, what we're going to say is if M equals MP1, then our TR is going to be given by this thing known as TNP. TNP is the no prying limit. So if we have a force less than TNP, there's no prying. But if we have a force greater than TNP, then we do have prying. So it's just a simple rearrangement here. We can see that TNP is equal to MP1 divided by B prime. So the only other thing that we need is the plastic moment capacity MP1. And so what we're going to do is we're going to look at a tributary width for each of the bolts that we have in this section. So for example, drawn right here, we have a tributary width right there associated with that particular bolt, and it's given the symbol P in this case. Now that tributary width is going to be determined by half your bolt spacing to each side, or if you run into the edge of a plate, that's obviously going to control your width. The maximum that you can go to each side is 1.75 B. So therefore we can find the plastic moment capacity MP1 just using plastic moment capacity for a plate. So this is phi times FU times 1/4 PT squared. Couple weird things with this equation. First of all, we're looking at FU, the ultimate stress. Most of the time when we look at plastic capacities, we use FY. The steel manual adopts FU because that lines up a little bit better with experimental data, and you do see a decent amount of strain hardening in these types of connections when you have prying. But if you want to use FY for yielding, be my guest. That is conservative, and that physically makes a little bit more sense than using the ultimate strength. The other thing that I'll mention is this phi factor is actually 0.9 because that is the phi factor for bending. So that's a different phi factor than what we use for the bolt itself. Either way, as long as you're adopting this equation for a plastic moment capacity, it gets subbed right in here. You have a moment arm, and that is the limit for when you need to consider prying action. So now let's say we do need to consider prying action. How do we do that? We're going to check the other two limit states, and the first one we'll look at is for bolt failure. So as I mentioned before, for bolt failure, we're assuming the force in the bolts is equal to the capacity of the bolt, TC. And you'll notice I positioned this once again at the edge of the bolt hole. And that's to account for the moment in that bolt as well. This distance is still going to be B prime right here. But now at these locations, because our force is greater than the no prying limit, we know that our moment here is MP1. So essentially we have yielded the sections right there. We'll have a prying force here of QR, and also on the other side, and our force that we're pulling on this assembly with is 2 times TBP, so the bolt prying failure load. To analyze this, we're going to look at the free body diagram for this section right here. So let me just draw that out over below here. So of course we have a moment on that section. So that is going to be an MP1, and we'll have a force up on that of TBP. And there's a force here of TC. That's the capacity of our bolt, and our prying force of QR. This distance is still B prime. And we're going to call this other distance here A prime. And that's therefore the distance from the edge of this hole over to the edge of your plate. now we just need to do some statics. So statics says sum of forces in the y directions better be equal to 0. So in this case, I have a QR plus TBP equals the bolt capacity TC. And we also have a sum of moments equal to 0. I'm going to do my sum of moments equation right here at the force TC. So if I do that, I'll find that TBP times the moment arm of B prime is equal to QR times the moment arm of A prime plus MP1. Now, in this case, we see that we have two equations, two unknowns. So my unknowns are the prying force and the failure load TBP. Shows up in both of these guys. So therefore, we can solve for both of the equations. And I'll write out just the one for TBP right here. So solving for TBP, we'll find that that is equal to the bolt capacity, TC, times the moment arm A prime, plus moment capacity MP1, divided by the distance A prime plus B. And that is therefore the load at which we get a bolt failure and not a plate failure when we have prying. Now let's look at our plate failure load. For the plate failure load, we're going to have 4 hinges, and 2 of these have MP1, and the other 2 are going to have MP2. MP2 is going to be slightly less than MP1, and it's accounting for the fact that there's going to be a hole in that section, so we're reducing our plastic moment capacity at that particular location. Our applied load up here is going to be 2 times TPP, which is our plate prying equation. And this is going to be QR, our prying force on both sides. And the bolt force, once again, we're going to put it at the edge of that bolt line. And what we're going to do is we're going to look at the free body diagram for just one of these sides here. So doing so, here is that section, and it has a dimension of B prime as always. That's the same as we've been looking at throughout the whole thing. And I'm going to have a moment MP1 on one side and a moment MP2 on the other side. And we're going to have a force of TPP on one side and a force of TPP on the other side. So doing a simple sum of moments gives us TPP is equal to MP1 plus MP2 divided by moment arm B prime. Nice. So that one's nice and straightforward. The only new thing that we have to do is evaluate MP2. So that's exactly the same as MP1, except we're going to subtract out the whole. So MP2 is going to be phi times FU, same as before. If you want to use FY to be conservative, that's fine, times 1/4. And instead of distance P, we're going to use P minus D prime times T squared. Now, this D prime is going to be the whole diameter. So that's essentially the section that we're subtracting out. We subtract out that width, we get a new plastic moment capacity that is reduced. And that will give us the plate failure load when we have prying. So to summarize the whole procedure, it's a 5-step procedure. First, we need to find our flange plastic moment MP1. Just recall that this phi is going to be equal to 0.9 because you're dealing with bending. And if you want to use Fy instead of Fu, be my guest. We'll then find the force at which we must consider prying. That's TNP. And if our demand TR is greater than TNP, then we have prying. And if you have prying, you have to move to step 3. If you don't have prying, you're done. You can just check your capacity in the traditional way. If we do have prying, there's 2 limit states that we need to check, bolt or plate failure, and the controlling one is going to be the minimum of those 2. So effectively what TC adjusted is going to be the bolt capacity that has now been adjusted to account for prying action. And this is always going to be less than your original TC to begin with. So let's put this into practice. So we're going to return back to our original example, and we're going to see if this works when we consider prying action. Specifically, we're going to be looking at the T section here. You can also look at the beam itself, and we'll discuss that at the very end. So going for that T, we have a WT 12 by 42. We can get all of our dimensions from table 1-8. The first thing that we're going to need is this flange thickness. That's going to be our dimension T. The other thing that we need is a bolt hole diameter. So this is going to be a standard hole, and we're doing 7/8 inch diameter bolts. So that means the hole diameter is 15/16 of an inch. I am not going to add a 1/16 of an inch onto that for the damage zone. And the reason I'm not going to do that is because that would actually reduce my moment arm, and that's not a conservative assumption for this case. So we're just going to use the hole diameter as it's specified in table J3.3. We'll also need the gauge length. This is 5.5 inches for a W12x42. We'll need a stem thickness of 0.47, and using all these numbers, we can determine distance B prime and A prime. So B prime is 2.046 and A prime is 2.229. Lastly, we need to find our tributary width for this bolt. So this is the B dimension here, and specifically we need 1.75 B, and that's calculated to be 4.4 inches. So we go over here and we look at our tributary width for each bolt, and we'll see that this distance here is given by 3.75. That's just half the spacing. 3.75 is less than 4.4, so I get to use the entire 3.75. And there's going to be a 2.25 up here. That also is less than my limiting 4.4 inches. So therefore, my P dimension is a total 6 inches, which is, of course, just half of my 12-inch section here. Given those dimensions, now let's crunch some numbers for this thing. So the first thing that we need is our plastic moment capacity. So we need a 0.9 for the phi factor. We need a FU. Let's assume it's a 992 steel. So this is 65 KSI. Width P is 6 inches and thickness T is 0.77 inches. And I'll square that divided by 4. And this is equal to 52.03 kip inches. So that's my plastic moment capacity. Therefore, my no prying limit is going to be that moment, 52.03 kip inches, divided by the moment arm of B prime, which we found was 2.046 inches. And this is 25.43 kips. That is less than my demand, TR per bolt, which is 37.5 kips. Therefore, I need to consider prying in the next step. So because my demand is greater than the prying limit, I will have prying on this connection. So given prying, let's calculate the two limits. I'll do the bolt one first. So TC, first of all, that's our bolt capacity. We already looked that up. That was 40.6 kips for our bolt. And dimension A prime is 2.229 inches, plus MP1, which we already know is 52.03 kip inches. Divide that by A prime, which was 2.229, plus B prime, 2.046. And we find that this is 33.34 kips. Now let's go to our next limit state, and I'm going to calculate my second plastic moment capacity at the hole location. So it works the same as before. I have a 0.9 phi factor and a 65 KSI ultimate stress. P is 6 inches, and I'm going to subtract off the hole diameter, which is 0.938 inches, and multiply by the thickness of 0.77 inches squared. And we're going to divide that by 4, and this capacity is 43.9 kip inches. Given that moment capacity, now I can add them together. So 52.03 kip inches plus 43.90 kip inches divided by B prime, which is once again 2.046 inches. And that gives me the plate failure load of 46.88 kips. So among the two, I see my bolt failure load controls. So I'm going to have a bolt failure in this connection, not a plate failure. And furthermore, that capacity is less than my demand of 37.5 kips. So this is not good. Our connection is going to fail in the bolts due to this combination of prying with the tension forces from before. Because we have a bolt failure, our best course of action here is probably to increase the bolt diameter. You can increase the plate thickness as well. That will decrease the amount of prying you have. It's probably not going to be quite as efficient though, because again, we did have a bolt controlling mechanism. So increasing this to a 1-inch diameter bolt is probably going to work. We'll have to check that out and see how it turns out. Now, the last thing is that I did mention, well, what about the beam itself? Is there going to be prying on that as well? And we should check that too. One of the nice things about the beam in this particular case is that the thickness here of the flange is actually a little bit thicker than the T section itself. And the B prime dimension is actually a little bit less because the web here is also a little bit thicker. So because your B prime is less and your thickness is more, generally speaking, that means your T section is going to control this section. So yes, we should check it, but we're going to find that bolt failure in the beam and plate failure in the beam are probably going to be higher than what we just saw in the T section. The other thing that I'll mention is that the A prime, even when you're checking that beam section, is going to be to the edge of the T section. And that's because you can't get a prying force way out here. The prying force is going to happen at this connection right here, QR, and A prime is technically the distance to the prying force, not always all the way to the edge of that beam. Lastly, there are 2 more limit states that we need to check for this beam because it is subjected to a concentrated tensile force. These are located in J10. Specifically, in this case, we need to investigate web yielding and also flange bending, but that is going to be a topic for a future video. So as always, I hope you learned something about prying action and bolt tension, and I will see you next time.